We are given a quadratic function, f of x equals a, x squared, plus b, x plus c, and two conditions. First, the graph is symmetric about the vertical line x equals -1. Second, for all real numbers x, the absolute value of the derivative, f prime of x, is less than or equal to 5x squared plus 15. Our goal is to find the maximum possible value of a that satisfies both conditions. Let's begin by using the symmetry information. Since the axis of symmetry is at x equals -1, we can write the function in vertex form as f of x equals a times the quantity x plus 1 squared plus k. Taking the derivative, we get f prime of x equals 2, a times the quantity x plus 1. So the inequality becomes the absolute value of 2, a times x plus 1, is less than or equal to 5x squared plus 15 for all x. To find the greatest possible value of a, we consider the limiting case where equality holds. Now, for simplicity, we'll assume that x plus 1 is greater than or equal to 0, and that a is positive. This lets us drop the absolute value, so the expression becomes just 2, a times x plus 1. To help visualize this, let's first look at the graph of g of x, which is 5x squared plus 15. This is an upward opening parabola with its lowest point at x equals 0 and a minimum value of 15. It grows rapidly as x moves away from 0 in either direction. Now let's look at the graph of f prime of x, which is a straight line with slope 2a. It passes through 0 when x equals -1 and increases linearly as x increases. This line represents the rate of change of our quadratic function. What we want is for this line to stay entirely beneath the parabola. That means the value of f prime of x, which is 2a times x plus 1, must always be less than or equal to g of x, which is 5x squared plus 15. The maximum possible value of a occurs at the point where the line and the parabola are just tangent. That is, they touch at exactly one point. Let's set up the equation for that situation. We equate the two expressions. 2, a times x, plus 1 equals 5x squared plus 15. Rewriting 5x squared minus 2, ax, minus 2, a plus 15 equals 0. This is a quadratic in x. If the graphs are tangent, then this equation has exactly one real solution, which means the discriminant is 0. Let's compute the discriminant. -2a squared gives 4. A squared minus 4 times 5 times the expression -2a plus 15, that expands to 4. A squared plus 40, a minus 300. Setting this equal to 0, 4, a squared plus 40, a minus 300 equals 0. Divide every term by 4, a squared, plus 10a minus 75 equals 0. Now solve for a using the quadratic formula. This is a quadratic equation in a. Instead of using the quadratic formula, we can factor it directly. We look for two numbers that multiply to -75 and add up to 10. Those numbers are 15 and -5. So the equation factors as a plus 15 times a minus 5 equals 0. So the two solutions are a equals 5 and a equals -15. But since we assumed a is positive, we take a equals 5. Therefore, the maximum possible value of a is 5.